Hello everyone. Have you ever been on a hot summer road trip and noticed a pool of water shimmering on the road ahead, only to realize it vanishes as you get closer? Or perhaps admired how brilliantly a diamond sparkles under light? These aren't just tricks of the eye, they are beautiful demonstrations of a single principle in physics called total internal reflection or TIR. In this session, we'll explore some fascinating consequences of total internal reflection, from mirages in deserts to fiber optic communication, and even the sparkle of diamonds. Let's begin with one of the most intriguing illusions, the desert mirage. Imagine you are standing in a desert or driving on a hot highway. The road ahead looks wet, almost like a mirror of the sky. But when you reach there, no water. This illusion is called a mirage. Here's what actually happens. On a hot day, the air near the ground is much hotter than the air above. Now, hotter air is less dense and has a lower refractive index than cooler air. So, when light rays from the sky travel downward, they bend gradually towards the denser, cooler air above. At a certain angle, the rays strike the boundary between cooler and hotter air at an angle greater than the critical angle. At this point, instead of bending further, they undergo total internal reflection and bounce upwards. Your eyes trace this reflected ray backward, and the brain interprets it as if the light is coming from the ground, making the road appear wet. As you can see in the ray diagram, the reflected light from the sky creates this beautiful but deceptive illusion of water. Now, have you ever looked at a cracked piece of glass or a test tube dipped in water and noticed how certain surfaces shine like a mirror? That shine is again due to total internal reflection. When light passes through the glass and strikes the boundary, say, between glass and air or glass and water, if the angle is greater than the critical angle, it gets completely reflected back inside. So instead of light escaping through, it is trapped and reflected, giving a shiny, mirror-like appearance. This is why an empty test tube partially immersed in water often appears bright when viewed from the side. A simple yet powerful reminder that the same principle behind the desert mirage also makes a glass surface sparkle. Alright, let's move on to something that always grabs attention, diamonds. Why do diamonds sparkle so brilliantly compared to other stones? The secret lies in their refractive index. A diamond has a refractive index of about 2.42, which is very high. This gives it a very small critical angle, roughly 24.4 degrees. So when light enters a diamond, it bounces around inside, undergoing multiple total internal reflections at its carefully cut surfaces. By the time it emerges, the light is split and scattered in many directions, giving that intense sparkle. That's also why jewelers cut diamonds at precise angles to ensure maximum total internal reflections. Physics, quite literally, is what makes a diamond shine. Now let's connect this principle to one of the greatest technological revolutions of our time, optical fibers. An optical fiber is simply a thin strand of glass. It has two layers, a central core surrounded by a cladding. The refractive index of the core is slightly higher than that of the cladding. When light enters the fiber, it strikes the core cladding boundary at an angle greater than the critical angle. As a result, the light gets trapped inside the core, bouncing back and forth due to total internal reflection. This allows light, and with it, information, to travel long distances with very little loss. That's how we get high-speed internet, fiber optic TV cables, and even medical endoscopy tools. A single principle of physics enabling the backbone of modern communication. Let's test this with a quick problem. Suppose we have an optical fiber with a core of refractive index 1.5 and cladding of refractive index 1.4. We want to find the maximum angle of incidence in air for which the light ray will be trapped inside the fiber by total internal reflection. Step 1. Find the critical angle at the core cladding boundary. We use the formula sin C equals n divided by n. That is sin C equals 1.4 divided by 1.5, which equals 0.933. So, C comes out to approximately 68.9 degrees. Step 2. Inside the fiber, the maximum angle with the axis is 90 degrees minus C, which is about 21.1 degrees. Step 3. Apply Snell's law at the air core interface. Sin I equals n multiplied by sin R, that is sin I equals 1.5 multiplied by sin of 21.1 degrees. This gives sin I approximately equal to 0.54. So, the maximum angle of incidence in air is the inverse sine of 0.54, which comes out to about 32.7 degrees. This means only if the light enters within this cone of acceptance will it remain trapped inside the fiber. As you can see in the diagram, the acceptance angle defines the efficiency of fiber transmission.
So to sum up, we've seen how total internal reflection explains many fascinating phenomena around us. Mirages in deserts and hot roads, nature's optical illusion, shiny cracks in glass and test tubes, small but striking effects of reflection, the brilliance of diamonds, physics adding value to beauty, and finally, optical fibers, revolutionizing communication and medicine. All of these diverse applications are governed by a single principle. When light strikes at angles greater than the critical angle, it cannot escape. It is completely reflected. I hope you now see how one elegant idea in physics ties together illusions, jewelry sparkle, and even your internet connection. Until next time, keep observing, keep questioning, because physics is everywhere around us.